Hello and namaste. In continuation with the partial differentiation, we have already started with the maxima minima of a function. We have completed the two different parts based on the maxima and minima. One of them is introduction with few questions. That was simple, but yes, they are very important to understand the concept of maxima and minima. Second session was little difficult level, and the third one is like a problem wherein it's like a word problem kind of. So we have to formulate and then we have to solve this for this function. Now for this particular, a rectangular box open at the top. So if you'll observe here, this is a rectangular box. If you'll observe, this is a rectangular box. It is opening at the top. To have a volume of 32 cc, that is cubic unit, find the dimensions of the box requiring least material for its construction. So this type of box we'll have to consider, wherein we have got this as the one side, this as the another side, this as the another side, this as the another side. So this two sides which are there in front of each other, they're having the same length and you can say a height or a breadth, you can say. So suppose for example, for this particular box, let this L be the length, B is the breadth, and H is the height for this particular box. So if you'll observe, this face is appeared two times. This face is appeared two times. So what is this face? If you wanted to have so let us go ahead. Let L, B and H be the length, breadth and height of the box respectively, and S is the surface area and V is the volume for that. So what we have to do it, we have to reduce or we have to minimize this surface area for the material construction. So this is we need to have the least material for the construction. If we wanted to have a least material for the construction, we should have the least area, or we are going ahead to minimize this surface area. Now V is 32 and LBH is nothing but 32, that is a volume, length, breadth, height is equals to 32. So B is nothing but 32 upon LB. S is what? It's 2 times L plus B into H plus LB. What do you mean by this particular statement? Everybody please check this here. What this particular statement tells us about it. So this is nothing but, you can check it here, which is nothing but 2LH plus 2 times BH plus LB. How this particular? So this, as I've told you, this face appeared for 2 times here. So this is L into H. So L into H has appeared 2 times. So 2 times L into H. Then B into H is again this yellow color face, and this yellow color face appeared for 2 times. But if you observe the base of this particular box, which is nothing but B into L. B into L. So it's LB here. B into L has appeared only once. We do not have the top of this particular box. We just have the base of this particular top box, and therefore this is nothing but what we have got it here. We have just taken this B into the consideration. B is equals to 32 upon LH. We have taken that value over here. After simplification, we'll get it. S is equals to 2L into H plus 64 by L plus 32 by H, and therefore differentiating with respect to L. So we are differentiating with respect to L. We are going to get it dou S upon dou L is equals to 2H minus 64 upon L square, because H would be the constant with respect to L. Similarly, we are differentiating partially with respect to H. We are going to get it dou S upon dou H is equals to 2L minus 32 upon H square. So we have got dou S upon dou L, dou S upon dou H. If we are equating now for the maxima minima of S, we have to equate them with a 0. After equating dou S upon dou L with 0, we are going to get it H is 32 upon L square. Dou S upon dou H, which is equals to 0, we are getting L equals to 16 upon H square. If we'll solve this equation simultaneously, that means suppose for example here, in this L, we are going to put the value of 16 upon H. So L is equals to 16 upon H square, and just by cross multiplication, you will get the values. All these values are L is equals to 4, H is 2 and B is equals to 4. After getting these values, we have to check whether these values L is 2, H is 2 and B equals to 4, are they giving us the minimum of this particular S? That condition could be checked out with this. So dou square S upon dou L square is this, nothing but, which is 128 upon 64, that is 2. Similarly, dou square S upon dou L dou H is 2. and dou square s upon dou h square is 64 upon h cube, that is equals to 8. And if you'll observe here, so it's nothing but RT minus S square. What is this? R means, R is this is S, and this is say for T. So RT minus S square, which is a condition of the existence of minima or maxima at the particular point. So we have got this particular point is equals to plus 12. That means what? If it is a plus, so this is nothing but plus 12. That means we got it as equals greater than 0. If it is greater than 0 means particular maxima or minima will exist at this particular point, 4, 2 and 4. But we have to check whether it's a maxima or minima. That can be checked it with the condition, that is R or R is less than or greater than 0, right? So now we have got this is greater than 0, because if you observe here, dou square s upon dou l square is 2. Similarly, dou square s upon dou h square is equals to 8. Both of them are going beyond 0. If they are going greater than 0, then s is minimum for this particular 3 values. This is about a problem question where we have to formulate a question, and then we have to go ahead and solve this particular question with using the maxima and minima concept. I hope you have understood this particular question very well. Thank you. Happy learning.